Hi there, what's up, Mister? I'm going to present my PowerPoint presentation on application of automata theory in game theory. So, let's begin. This is the introduction, the abstract of the whole presentation. Game theory is a framework for understanding choice in situations among competing players. Game theory can help players reach the optimal decision making when confronted by independent and competing actors in a strategy setting. Now, talking about the automata theory is the study of abstract machines and automata, as well as the computational problems that can be solved using them. The word automata comes from a Greek word which means self-acting, self-willed, self-moving. In game theory, presenting players with strategies directly affects the performance of players. It is found that finite automata, definite automata, adaptive automata, and cellular automata are widely adopted in game theory. In contrast, adaptive automata and cellular automata are intensively applied in complex environments where the number of interacted players is high, that is, the human, the computer application, etc. And therefore, the complex strategies are needed in these. Moving forward, let's talk about game and the components of it. So the first which we are going to talk about is the players. It is where the one side tries to maximize the gain, that is the payoff, and the other tries to minimize the opponent's score. However, these players can be humans, computer applications, or other entities. Talking about the environment, this includes the board position and the possible moves of the players. Now let's talk about the successor function. This includes the actions and returns a list of pairs where each pair indicates a legal move and the resulting state. Moving forward, talking about the terminal test. The terminal test specifies when the game is over and the terminal state is reached. Now talking about the utility function. The utility function is the numeric value of the terminal state. Let's talk about the introduction to the game theory. Any problem which are interacted with participants and actions that can be treated as a game. Let's suppose a car driver puts a plan to drive a car in a heavy traffic. It can be considered as a driving game. When a user bids on a bidding-based website, it can be considered as an auctioning game. Similarly, when an owner of a factory decides the price of his product, it can be considered as an economic game. Obviously, game theory can be presented in a wide range of applications. Game theory is basically a mathematical tool that can analyze the interactions between individuals strategically. Moving forward, the attractive point of this study of studying games is that models used in games are applicable to be used in real life situations. For example, in computer science, it includes interface design, network routing, load sharing, and allocate resource. It allocates resources in distributed systems and information and services transactions or internet. Uh, Different studies have found the different techniques that are used to return players' behavior in different games. One of the successful techniques used here in automata model is to represent and control participated agents. Moving forward, let's talk about the automata theory a bit. Automaton is a self-operating machine. As talked earlier, it comes from a Greek word and all. The output of an automaton is a combination between the consequences of the current input and the history of machine's previous input. A automaton is designed to automatically follow a predetermined sequence of operations or respond to encoded instructions. A learning automaton operates in a random environment. Like, it doesn't require any specific environment. The actions are chosen based on the inputs received from the environment to find the optimal result. The learning schemes come in two structures, that is the fixed and the variable structure. However, learning automation has a finite number of output actions, one of which is selected at each instance. Every selected action will be either rewarded or punished by the environment, which leads to the update of the probability distribution over the actions. Moving forward, let's talk about the automated types a bit. First is the finite state automaton. The finite state automaton is one of the well-studied computation models in theoretical computer science. The finite state automatons are composed of fixed finite memory, which takes a decision using the finite memory, a finite non-empty alphabet, a transition function, an initial state, and a set of final states. Finite automata are classified into deterministic finite automaton DFA and non-deterministic finite automaton that is NFA. DFA is only permitted to be in one state at any time. On the other hand, NFA can be in two or more states at any given time. Technically saying, adding restrictions to DFA is sufficient to transform it to an NFA. Let's talk a bit about the finite automata then. Transducers. Transducers. Transducers are automata which generate new output based on a given input or a state using its action. Transducers basically come in two types, that is the Moore machines and the Mealy machines. In the Moore machines, the outputs only depends on the state, whereas in Mealy machine, it depends on the input and as well as the state. Mealy machine is efficient in reducing the number of states. Finite automata are widely used in game theory. For instance, in the iterated and prisoner's dilemma, that is INPPD, finite automata can be used to represent the player's strategies there. The automata states represent the player's action and the input is the strategic profile observed from the other players. Moving forward, let's talk a bit about the push-down automata. That's the second type of automata we're going to discuss today. The push-down automata are finite automata equipped with stack. Several operations can be performed here, including the read, push, and pop operations. Let's talk a bit about the Turing machine. A Turing machine is an abstract computing device which consists of finite control, unbounded memory, and a finite program. The program is a list of instructions that guides the machine to take actions based on the current state of its finite control and bits in its current window on the information of tapes. Moving forward, let's talk about the third type of automata we're going to study today. That's the adaptive automata. So, what is it? Many studies have been conducted on this field. The attention on such studies come from the suitability of those systems in modeling any real-world complex system. In typical LA, that is the learning automata systems, a self-operating machine responds to a sequence of actions to achieve a specific goal. The automaton in turn may respond based on predeterministic rules or it may adapt to its environmental dynamics. In other words, adaptive automata is flexible and adaptive. So let's continue from where we got disconnected. So we're talking about the learning automata systems. The automaton in turn here may respond based on the predeterministic rule or it may also adapt to the environmental dynamics. In other words, adaptive actions are attached to the state transition rules of the adaptive automata and they're activated whenever the transition is applied by removing or inserting new elements to the automaton's transition set. Moving forward, let's talk a bit about the cellular automata. That's the fourth type of automation we want to talk about today. The structure of cellular automata is based on lattice of cells, where each cell may be a predetermined number of discrete states. Updating the states of CA in each time requires a predeterministic process of the neighborhood relation, indicating the communication structure between the cells. Cellular automata are considered easy to implement and emulate on a computer. In addition, C exhibits a wide range of possible non-linear outcomes. So, as we're talking about the cellular automata, let's move to the next slide. So, now we're going to talk about the stochastic automata. It's a bit different from what we've learned till now. Stochastic learning automaton can be defined as an element which interacts with a random environment to improve a specified performance. This is possible by changing the automaton actions probabilities based on the response received from the corresponding environment. The automaton starts with no information about the optimal action. The probabilities are equally attached to all. One action is selected at a time, and based on the response of the environment, the action probabilities are changed. Moving forward, let's talk about the application of automata in game theory. Application of finite automata. So back in 1985, Neyman tried to model the fact that players do only bounded computation by modeling the iterated prisoner's dilemma players as a finite automata. Again, it was continued only later by Rubinstein. So this was the history and all. Let's talk about some recent stuff now. Recently, finite automata have been widely used to represent player strategies in game theory. For instance, the researchers of what mentioned in Bo and 2004 have conducted several experiments, and the results showed that finite automata have significantly improved the performance of n-player prisoners dilemma. The study in May 2008 showed that infinitely repeated games such as Prisoner's Dilemma and Matching Peonies have performed in learning and presenting new strategies. Therefore, the study introduced dynamic systems where agents start the game with randomly choosing strategies which are represented by finite state automata. The agents also allowed to change their strategies during the game. Moving forward to the applications of adaptive automata. So, adaptive automata based devices have been presented as powerful tools for defining complex languages. The work presented in Gambit 2006 has paid more attention to the iterated prisoner's dilemma. An original evaluative probabilistic automation was created for strategy modeling. It has been shown that genetic automata are well adapted to model adaptive strategies. As a result, we have noticed that modeling the player's behavior needs some adaptive attributes. However, the computable models related to genetic automata are good tools to model such adaptive strategy. The work presented in Design 2009 was formed the collection of automata in tree-like structures and modification of the action possibility continued at different levels according to the reward signs provided for all hierarchical levels. Another work has been presented in 2002 which focused on the models which can be used for stimulating business dilemma. In addition, the work showed that genetic operators and probabilistic automata enable the adaptive behavior to be modeled for business dilemma strategies. Adaptive automata have computational power equivalent to a Turing machine. Moving forward, let's talk about the applications of cellular automata here. So, cellular automata can be complex systems by themselves, or they can offer ways of studying the behavior of complex systems. Cellular automata have been used to stimulate agents with different strategies. In that work, the researchers showed that the ability of evolutionary learning used to evolve cooperative strategies in structured population using n-player iterative systems. In addition, they examined both of effects of both fixed and random neighborhood. Stimulating the n-player iterative business dilemma as a betting game using cellular automata is one way of incorporating cellular automata in game theory. We can conclude that representing the behavior of n-players business dilemma models using cellular automata has a great benefit, since most of the researchers can utilize it to distinguish the effects of neighborhood structure on the evolution of cooperative behavior. Moving forward, let's conclude this. It's getting very long already. So, presenting players' game strategies in game theory is one of the factors which affect the player's performance significantly. In this work, we've analyzed the characteristics and the underlying structure of existing types of automata. Consequently, we've explored the applications of automata in game theory. However, the study revealed that only few types of automata have been utilized in game theory. We found that finite automata have been very widely used to represent simple agents' behavior. On the other hand, adaptive automata and cellular automata are mainly used to represent complex agents' behavior. The complexity level of both adaptive automata and cellular automata is determined by the number of states in the automata. The more the number of states were, the higher the capability of this automata to handle complex studies. So that was my time. Thank you for having patient hearing. I hope this video is informative for you. Thank you.